Okay, so we're looking at Unit 3.9 practice problems, starting off with a chromatography question. Now, this isn't actually paper chromatography. This is what is called thin layer chromatography, which I think you're going to be doing in AP Bio if you take that. I know she does some kind of chromatography. Anyway, so these things don't necessarily have a color, which is just as well. We wouldn't be able to see it if they did. Here's what we have. We have a stationary phase that, here looks like it could be a piece of paper. And we've got a dot that contains these three liquids placed here at the origin. We don't know what the solvent is, but as the solvent came from underneath that line and moved up the paper, the components of this dot broke apart into three separate dots on the paper. You will see that we've got hexane on top, then dimethyl ether, then ethanoic acid. So what we need to do, we're trying to figure out, is the stationary phase polar or nonpolar? Is the mobile phase polar or nonpolar? And the way to do that is to see what these different components of the liquid did as they jumped out of the mobile phase onto the stationary phase. So the idea here is which of these is the most polar, which is the least polar. Right off the bat, I can see hexane over here is nonpolar. Straight carbon chains like that are nothing but carbon and hydrogen are always nonpolar. That's a nonpolar molecule. And it stayed in the mobile phase pretty much as long as it could. Looking at diethyl ether and ethanoic acid, I noticed that ethanoic acid is capable of hydrogen bonding. So that means it is pretty polar. It's very polar. Diethyl ether, is, remember, definitely not shaped like they've drawn it. They made it look linear, but this oxygen is sp3 hybridized. We've got a bond angle right there in the middle of that thing. This is a polar molecule, but not capable of hydrogen bonding. Definitely, though, dipole-dipole attractions. So if I had to say which of these two is the most polar, I'm going with the guy who is capable of hydrogen bonding. So ethanoic acid is most polar. Diethyl ether is polar, just not the most. So the most polar one got out of the mobile phase as quickly as possible and was attracted to the stationary phase. That tells me the stationary phase is polar. On the other hand, the hexane, the nonpolar molecule, rode up the solvent as pretty much as far as it could before coming out of the solvent and depositing onto the paper. The hexane is nonpolar. That tells me that the mobile phase is nonpolar. At the very least, I would expect these two to be opposite. That's the way chromatography works. It can't, B and C kind of don't make any sense. They have to be opposite in polarity. Okay, hope that made sense. Maybe we'll see another one. I've got to figure out how to turn the page. Come on. I know there's more than one question here. There's a bunch of questions. There we go. Uh-oh. But I don't see the beginning of the question. Okay, let's just read this. Okay, so the chemist is studying these two compounds. Okay, I'm not sure. I don't know what the question's going to be, but this guy right here, nothing but a bunch of carbon-hydrogen bonds. I'm going to go with he's either nonpolar or maybe based on his shape, he's got a little polarity, but I'm not expecting much. This guy is polar, and specifically I see that hydrogen is capable of hydrogen bonding. Okay, so the chemist is going to use chromatography to separate those two, obtaining the results shown in the diagram. The mixture was separated by a polar stationary phase and a nonpolar mobile phase. Okay, so the mobile phase, it said, was nonpolar. Mobile phase is nonpolar. and the no nonpolar, and the paper itself, whatever it may be, is polar. Based on the chromatogram, the chemist claims that the spot labeled 1 corresponds to, this is the ethanoic acid. He's saying that that guy is the acid, and that the other spot must be there for the nonpolar molecule. Which of the following statements best supports his claim? Okay, I am seeing if it's a nonpolar mobile phase, then the nonpolar molecule would stay in there longer. So I agree that the dot 2 is the nonpolar one, dot 1 therefore is the ethanoic acid. That's because the paper itself is polar. Let's see, I kind of like A. The methanoic acid has a stronger interaction with the stationary phase than the other guy does. He definitely does. B is out. It says he has a weaker. If that acid is number 1, then it has a stronger attraction to the stationary phase. It's true that they may be heavier. I don't know. I'd have to add up molar masses. I think they do give them over there. It doesn't matter. Has nothing to do with the surface area either. So yes, I'd say the answer here is A. Okay, what a pain in the butt this is. A chemist wants to prepare 10 liters of 0.05 molarity of the acid. Approximately how many grams should he use? I'm going to show you how you would do it. I hope you can do this yourself. Moles is molarity times liters, so 0.050 molarity times 10 liters. That would be 0.5 moles. And we would multiply that by the molar mass, which they're telling me is 102. Okay, we can do this, 102 grams per mole. So I'm expecting the one that is around 0.551. Yeah, looks like it's that. Okay, which of the following identifies the compound expected to have the higher boiling point and best explains why? Looking back over at these things, I'm expecting the guy with hydrogen bonding, that's a stronger intermolecular force, to have the higher boiling point. So I'm ruling out A and B, and I'm focusing on C or D, and it's D. It's the acid because it can form hydrogen bonds, and the other guy can't. Okay, so here they're giving us some properties. This is methyl alcohol, and this is water, obviously. A student's given a beaker containing a solution of methyl alcohol and water, and wishes to separate and collect the two components. Which is the best way to do it? We've got two different boiling points. I would use distillation. If we start heating it up, when we get to 65 degrees C, the methyl alcohol is going to boil off. If you keep going to 100 degrees C, then the water would boil off. But what you would do is boil off the methyl alcohol and leave the water. This is how an old-fashioned still used to work, you know, when people used to make their own alcohol. Okay, so here we go. Boiling the mixture and condensing and collecting the first vapors produced. That is distillation. Looking to see if anything... Okay, this whole paper chromatography, you're never going to completely separate the entire solution. It's more like, here's a little dot of this stuff. Let's see what's in there. But you're not separating the whole thing. With distillation, you're separating the whole thing. Okay, let's look at number 6. Again, we're going to separate these two things. Again, I see two different boiling points. Again, I want to distill them. Let's see. D says distillation because the liquids boil at different temperatures owing to the difference in strength of their intermolecular forces. Yes, and here, if you look at these two guys, they're both just carbon-hydrogen compounds. They're non-polar. The strength of the intermolecular forces is all about the size of the electron cloud. The strength of their dispersion forces. So yes, this is octane. He has a bigger electron cloud, stronger intermolecular forces, higher boiling point. And the answer here is D. Ooh, this is column chromatography where you actually can separate these things. They're placing an aqueous mixture of X and Z into this column that is packed with a nonpolar stationary phase. Okay, so all of these circles here are considered to be the stationary phase. And in this case, those circles are nonpolar. That must mean that, okay, so you put the X's and the X and Z there. It's a mixture of liquids. And then you pour ethanol through it. Ethanol is going to be, okay, the circles are the stationary phase and they're nonpolar. Ethanol is going to be the mobile phase, and it is polar. See that O right there? And the H, hydrogen bonding. Okay, so this is before the ethanol is added, and this is after the ethanol is added. And what I'm seeing is all of the X seems to be attracted to that nonpolar stationary phase. See, everything started up there, and then as soon as it starts coming out, all of the little X pieces are heading to that nonpolar stationary phase, whereas down here, after the ethanol passes through, the Z's are left down here. They rode the polar phase down, the polar mobile phase down the column as far as they could. So I think that the X's are nonpolar and Z's are polar. Let's see. X is more polar than Z? I don't think so. X has smaller molecular volume, doesn't matter. Z is more polar than X. Molecules of Z are more attracted to the mobile phase than to the stationary phase, and that's what we're seeing here. They rode the mobile phase down the column and then finally had to get off at the end. Whereas X, as soon as it hit as soon as it started coming into the stationary phase, they all jumped out. They're nonpolar. The Z's are polar. And again, the larger molar mass doesn't matter at all. And that was it. Okay, thanks, guys.